Okay, it's 10. Our first presenter is going to talk about FenaiBot, the precision 3D crop phenotype typing robot for greenhouse. Please.
Good morning, everyone. My name is Iván Pérez Oliveras. I'm part of the Machine Vision and Optical Sensing Laboratory at South Dakota State University. And I'm also currently work as a crop phenotyping engineer at Inari. So I presented the advances in this project that is called FenaiBot, a precision 3D crop phenotyping robot for greenhouse. So phenotyping is a quantification of this dynamic interaction between the genetic background of an organism and its surrounding environment. So this interaction is of particular interest for breeders to develop new varieties that are resilient to different kind of stresses. So in the last year, we have seen many advances on developing new phenotyping platforms because quite often these measurements are done manually. So usually they are time-consuming, labor-intensive, and often destructive. So there is a gap between reaching the same piece of genotyping that is faster and is getting every day cheaper. So developing new platforms to reach this piece that we can combine this information to create all these new crop varieties. So in this project we are testing this FenaiBot on chili pepper. As you can see from this graph, there is a clear tendency on the domestic production of that is decreasing in the US. So with this project we can potentially use the information of this phenotyping robot to develop new varieties that are more appealing for farmers or for the market, or that can be easy to harvest or resistant to different kind of stresses, etc. As this is also a highly valued crop, so the market is valued around $100 million. And as you can see from this image, it's also highly diverse, so it's easy to detect this difference between the different varieties. And it's a good example of how we can combine different varieties to develop new varieties and can reach the requirements of the market of farmers. So the objective of this project is to develop and evaluate the FenaiBot, an autonomous robotic system for 3D crop phenotyping of pepper varieties in greenhouse settings, and also to assess the accuracy and efficiency of this FenaiBot in measuring three phenotypic traits that are plant height, crown area, and leaf count per plant for pepper varieties. So our hypothesis is that the FenaiBot can accurately and efficiently measure these key phenotypic traits autonomously with measurement accuracy comparable to ground truth data or manual measurements. So this is a quick overview of the FenaiBot. It is based on the Wiltec Robot developers platform for research and industry. So in this robot, we are attaching an Intel RealSense D435 as our main phenotyping sensor. It is a RGBD camera that can capture colorful images and also depth information about the structure of the canopy, so we can combine this information to make a 3D representation of model of the plant on which we can extract or phenotypic traits. It also has other sensors to add to the autonomous navigation system, like a LiDAR, 2D LiDAR to detect the surroundings, and another RGBD camera for navigation, and also another RGB camera that is mounted on the side to be able to detect each pot that we are measuring or capturing data. So all this information goes into a computing edge device that is a Jetson Nano Orient that is in constant communication with the actuator through an STM32-based controller. So the experiment on which we test this FenaiBot is was a randomized split design of 4 pepper varieties with 6 replicates in a greenhouse located in South Dakota State University in Brookings, South Dakota. And the 4 pepper varieties that we tested were Poblano, Thai Hot, Hungarian Hot Wax, and Black Hungarian. We collect 4 data sets at 44, 52, 57, and 69 days after planting. So the workflow for this FENAIBOT is divided in 3 steps. The first one is data collection. So we are taking this robot to the greenhouse and start the data collection step by moving the robot and detecting each spot by reading the information that is embedded in a QR code that contains the variety name and the replication number. So we are tagging all this information into a set of 20 to 30 images and point cloud data. Then we are downloading this data into another computer system to the data processing step, where we are extracting for the RGB images the number of leaves per plant and calculating also the crop major and minor diameters to estimate the leaf area, the canopy area, and from the point cloud we are calculating the plant height. So the first methodology that we are using to calculate the plant height is an adapted version of this method that was reported by Jimenez Berni at 2018. That is based on the frequency distribution of points in the field direction of the point cloud. As you can see in this diagram, we are defining the plant height of the distance from the ground or reference plane to the highest part of the canopy. So we are considering our ground plane as the highest point in the histogram or the mouth of this histogram. As you can see, there is a big blue patch in this point cloud. So by having this distance that I named here as HG, we can subtract this distance from the point cloud in the direction. So by doing some testing, we found that the 95 percentile of these plant height points can tell us which is the highest point in the canopy, so we are considering that as the height of the plant. And also, we are implementing a YOLO object detection and segmentation model in order to segment the canopy of the plant and extract then the other traits we are looking for. So YOLO is a well-known architecture for object detection that nowadays also have some instant segmentation capabilities. So this architecture in the backbone can extract these visual features of the images. The next can upscale also some smaller details. And finally, the head creates 3 different it creates a bounding box at 3 different scales with a confidence score. So the metric that we're using to evaluate the performance of the FENAIBOT are the R-squared and mean square error for comparing the manual measurements with the information that we get from the FENAIBOT, and precision recall and MEP50 for the canopy detection and segmentation. So some of the results that we're getting now from this project is from the plant height. As you can see in this graph, for the 4 growth stages that we measure, we are capturing effectively the tendence of the median value of the plant height going higher. So we are capturing how the plant is growing across all of the different physiological stages. And also we are capturing that there is a difference between these 4 paper varieties. So as you can see, in each box plot has a different median value and also different variances. But as you can see in the last 2 days, there is more variance that can be explained because as the plant is growing, there is more occlusion between the leaves, and also the area of the effective area that the Fenibot can cover doesn't fit on, to the whole plant. So, so as you can see, there is a more improvement there to being able to capture more area and also to solve this problem with occlusion. But overall, the performance of the Fenibots compared to the manual measurements, at least for measuring the plant height, is really good. We are getting an error square value what is highly correlated, so we are getting also an error square value around above 0.9, and with a low RMS square RMS error of below 0.05. So this is also the result of the training the YOLO Nano segmentation model. This model was trained over 1,000 iterations. So based on the recall and precision curves, we can see that the model is converging around 350 iterations. Also, from the precision and recall curves for the detection model on the left and the segmentation model on the right side, we can tell that with 50% of confidence that the detection and segmentation that we are doing with this model is around 0.93 or 93%. And also from the confusion matrix, we can effectively say that at least the mask that we are using for segmentation is accurate in 92%. So in conclusion, the Fenibot is able to measure these phenotypic traits with accuracy comparable to run-through data or manual measurements. So these findings could potentially increase the capacity of breeding programs on developing varieties resilient to current global biotic and abiotic stresses, and also the combination of AI and traditional analytical models or methods can be combined to reach this goal. But also this project has potential application not only for breeding, but also for crop scouting that can be more useful for farmers in a daily basis. So future work using the Fenibot to measure, we will use the Fenibot to measure phenotypic traits, coverage area, leaf area index, or leaf counting, and we're planning to scale the system to measure other crops in field conditions that are more representative for the Midwest area that are grown corn and soybean. So you can see we have this platform that is a FarmAP Amiga robotic platform for spraying and phenotyping, and also there is a parallel project on soybean phenotyping in the greenhouse. So I would like to acknowledge thank to my other lab members, and also to the USDA NIFA TC grant. So thank you for your time.
We have a little time for a couple of quick questions.
Thank you for the presentation. Actually, I have a few questions. One of them is that you showed a couple of sensors at the beginning. IMU, LiDAR, one depth camera, plus we have real sense camera. Yes, right. So here we have our perception system that you're saying real sense, LiDAR, Astra S, what's that, RVCAM. On the other side, we have I and you. So the first question is that, did you utilize all these sensors?
Absolutely.
Did you use all these sensors in the robot?
We were more focused on using the interreal sense to do the phenotypic inspection, and the other sensors are mostly used to try to achieve this autonomous navigation task.
Autonomous navigation.
So yeah, we are combining also the information from these sensors.
So data comes from interreal sense camera. The point cloud data and RGB comes from interreal
It
sense.
comes from the interior sense.
But you have used LiDAR and other cameras plus IMU for navigation.
Mostly for navigation, yeah.
Have you utilized all those sensors for navigation?
Not yet.
Fuse? Not yet.
Some of them.
Some of them?
Yeah.
Okay. And the next question is that in the interreal sense camera that you showed already data, you had point cloud data, you had RGB data, and you showed something for, so here we have point cloud data. If you go to the other slides, we have one thing that we push right here. With YOLO segmentation, you can segment out those leaves, and ultimately you want to estimate the height of the plants, right? So what is the connection between this leaf segmentation and height estimation? How do you make that pipeline to get information from this YOLO and then take the point cloud data and then estimate the height? You know what I mean?
Can we discuss that afterwards? They put us so packed that I have to move on. If you don't mind, let's discuss that next time. Thank you again. Faraz. Thank you very much.
So,
Yes, it works. Okay, next talk, autonomous robotic navigation in ornamental crab production using vision and sensor fusion. Please go ahead.
Okay, so before I start, I have a question for all of you. How many of you are familiar with self-driving cars? Just show of hand. Self-driving cars. Okay. What about Roomba, those small cleaning robots? Okay, there's a lot of them. So these are the two examples of autonomous robots. Today we will be seeing development of an intelligent navigation system for another autonomous robot that works in a nursery. Welcome everyone, I'm Faraz Ahmad. I'm a master's student at Open University and I will be presenting my research work on autonomous robotic navigation and ornamental crop production using vision and sensor fusion. So the biggest question is, why do we need autonomous navigation in ornamental crop industry? So do you know the ornamental crop nursery industry in US is $160 billion industry, and this is from 2018 statistic, and it has gone up. But the biggest problem they are facing is the labor cost and shortage. So first of all, 35 to 40% of the total expenses goes to labor to cover the labor cost. Also, they are facing the labor shortage, due to which they are not able to scale. Not only scale, but also they are not meeting the current demand of the market, which is increasing. So to tackle this, USDA spent $287 million supporting 213 research and development projects to do the automation in ornamental industry. And as a result, many of the key processes that is done in the nursery has been automated, or some of them are in the process of being automated. But most of these platforms are usually mounted on a robotic platform, and that robotic platform still has to be driven by a human. So we are not fully autonomous unless we can make those robotics system autonomous. For that, we need to develop an autonomous navigation system. So going back to literature, we found out that autonomous navigation in agriculture industry is not a new subject. There is a lot of application, and some of the commercial products also available, tractor, autonomous tractor in open field, that do these things. The gap exists that there is almost no autonomous navigation in ornamental industry. And the challenge is the ornamental industry structure is different than other agriculture scenes, due to which it needs its own autonomous navigation system. Objective of this research was to compare multiple intra-bed navigation. So intra-bed navigation refers to when the robot is moving in a single bed. So first objective was to compare multiple intra-bed navigation techniques. Second was to find which technique is best for ornamental industry. Third was develop inter-bed navigation. So this is two-part problem. One is intra-bed when the robot is moving in a single bed. Inter-bed when the robot moves from one bed to another bed. Then we also developed a digital twin and we tested and validated these algorithms and then achieve complete autonomy. So by integrating intra-bed navigation and inter-bed navigation, we achieve the complete autonomy. So let's dive into the material and methodology. This system was the combination and integration of electrical, mechanical, software and AI. The hardware that we use is listed down here. The robot we used was from firm NG Amiga, modified for nursery, which we call nursery board. The primary sensor that we used was Z2 camera. For our vision sensor, we had a portable monitor right in front of this robot. We used Jetson Nano AGX Orin as our primary computer. We had some sonar sensor mounted on the wheels for distance measurement and Adafruit feather and fork for communicating between Jetson and our nursery board. So, as I mentioned, there are two parts of the navigation. One was intra-bed navigation and second was inter-bed navigation. So, for intra-bed navigation, after doing the literature review, we found out these are the 5 most common classic computer vision algorithm that has been used to solve the similar issue in other agriculture scene. So, this was some of the algorithm we tested, and then we developed our own custom framework, especially for ornamental plant industry, which we are calling StrideNet, and it has 2 versions, Nano and Medium. Here is one example of how we modified the classical computer vision algorithm for our application, because the ornamental industry ornamental structure was different, so we could not use the way they developed for their application. We had to modify it for our application. This is one example. So we used a depth image for this one. Depth image was used to reduce the effects of lightning, shadow, that kind of effect. So we had the depth image, then we applied the apply technique to increase the contrast. Then we apply the gain edge detection to find the edges, all the edges. Then we apply the region of interest for left boundary, left edge of the bed and right edge of the bed. And once we had this, we filter out the points and use line fitting techniques. For this one, we use RenSec. And from this left and right lines, we found out the center line that we compared with the center of the image. We found out the deviation. Robot need to align itself right in the center. This is one example. This similar structure follow for all the other 5 examples, so I'm not going to show it. Then we had developed our own custom framework, which we call StrideNet, stand for Segmented Topological Recognition and Instant Detection, Edge Detection. For that we went to the field and we collected 6,000 data points. We used ROS2 for all our navigation system. Here is the ROS graph for data collection. Then we trained a YOLO model. The YOLO model we used was YOLO V8 segmentation, and it has 2 models that we use, Nano and Medium. And here are some of the examples. So basically we collected 9 different classes of the data depending on different situation, lightning, indoor, outdoor, everything. And then we trained the YOLO model. Once we had the YOLO model trained, then we apply the classical computer vision algorithm for edge detection. So what we did is we combine what AI and deep learning has to offer and what it is good in, and then we combine what classical computer vision has to offer and their strength, and then we develop a framework for this. So here you can see a demo. So on the right side we are doing some field testing, some lab work, and on the left side you can see the StrideNet in action. So the StrideNet is giving output the angular deviation. So how does it work? So basically we are using the RGB data. Then I already showed that we train a YOLO model. We train the YOLO, we pass it through the YOLO model, and we get the bed spacing. So this bed spacing refers to the space between 2 adjacent beds. Once we had it, we find out the contour of these, and then we find the principal orientation line of these contours. And then once we had those contours, we only keep the edges that we are interested in and remove the other parts. And from that we use the line fitting techniques to fit the lines for these, and then we find the intersection point for these lines. And so once we have that point, we find the angular deviation the robot needs to align itself in the center. So that's how the stride net works. Now that was the one part of the navigation. Second part, much easier, but there is a second part which is interbed navigation. So once the robot reaches at the end of the bed, it has to move to the next bed. That's what we call interbed navigation. And it has two components. One was robot localization and second was path following. So robot localization means where the robot is after some time, not only its position but also its orientation. And why we need this? Because it was very challenging to align the robot to the next bed exactly. And the challenge is if it wasn't perfectly aligned, when the intra-bed navigation kicks in, it could actually collide with the next bed. So we had to avoid this. Second part was path following. So we had a predefined waypoints and the robot has to accurately follow those waypoints. So here's the control system for that. You can see we have IMU data and visual odometry which we use to find the accurate location of the location and orientation of the robot, which was fed as a feedback loop system. Then we had goal position, which was a predefined waypoints for the robot, and we used P2P control system, which is point-to-point controller system, which calculated the linear angular velocity for robot to follow. So that was our inter-bed navigation. Once we had solved our intra-bed navigation and our inter-bed navigation, last part of the puzzle was to integrate both of them and achieve complete autonomy. Now coming to the results, one of the key and most important metrics once we started working on the robot was stability analysis. So the stability analysis has two parameters. One was first order MAD and second was second order MAD. First order MAD was referring to acceleration. So as you know, the algorithm gave us the velocity value. So first order MAD, which is mean average difference, mean the acceleration value, and second order MAD, which is jerk value. So what we need to find an algorithm that is more stable, that can give you the velocity and that can give you the smoothest values. So you can see the whole transform one has the highest MAD value. That it means that it is least stable, which would cause the robot to like randomly take turns, which can drain out the battery very easily, which can damage the component and reduce the lifetime. So what we wanted to do is see the least value. So here you can see the proposed custom framework for ornamental industry is the highly stable algorithm. The next was computational efficiency. So we want this autonomous navigation will be working real time. So for that we need to find will it be able to work in real time. For that we did FPS analysis, which is frame per second analysis, and we conducted it on the same computer that we use in the field. And you can see that there is the graph for that, and you can see that in this graph, our transform has the highest FPS value. So it means that because of its simplicity, it can process more frame per second. On the other hand, the Kenny edge detection plus least square method has the slowest frame per second. So it means that it can process low frame per second. And on our algorithm has done outperform the Kenny edge detection. The last part was algorithm selection. So for that we plotted FPS and first order MAD against each other. Here you can see the whole transform can process a lot of frame, but it's also very unstable. Contour has the same issue, it's also unstable. The Kenny edge detection is slightly unstable, but it falls below our minimum FPS requirement for the robot to work in real time. And our StradNet, the proposed StradNet, was able to perform well on the FPS side and also was highly stable. So conclusion, we developed the different intra-bed navigation algorithm from classical computer vision and StradNet, and then we compared and identified the best performing algorithm. And then we designed an inter-bit navigation between for robot to move from one bit to another bit. Then we achieved the complete autonomy by integrating these two. Future work, currently we are doing some field testing, so we want to finish there. And in the future, we want to be able to do the global path planning and navigation for robot to move around the whole nursery. I'm thankful for USDA and Department of Biosystem Engineering for funding this project. This is some of my references. And that's all for me. If you guys have any question or suggestion, I'm open there.
Thank you. Maybe one very quick question, if there is any. If there is not, then the next speaker, please. And then you guys, the area is not too huge, so I would say really communicate also afterwards. So our next talk is an introduction to the MAPS and its potential for the development of agricultural autonomous and AI systems.
All right, good morning. So my name is Kodai Watanabe. I'm a first year student at MSU. Today's presentation is about the introduction to MAPS, which is an off-road vehicle simulator, and which stands for Mississippi State University Autonomous Vehicle Simulator. Today's goal of this presentation is to show you what you can do with this MAPS simulator in agricultural scenarios, and also I would like to kind of encourage you to use the simulator and to contribute to the GitHub repository. So to achieve the goal, we have two items on the agenda. So first, basically, I spend most of the time on the what MAPS is or what MAPS can do. And if time allows, I'd like to kind of touch a list of the top research topics that I'm working on using MAPS. All right, let's dive in. So, let's start with the basic question, why do we need simulation, right? So when it comes to the development of the AI and autonomous system, there are big problems, there are time-consuming and labor-intensive activities, which are mainly caused by data collection and performance evaluation of whatever algorithms you want to test in the field. And the question is, can we alleviate those problems? And the answer is yes. And we can do so by transferring those tasks from the field to the simulation environment. And then here, especially I'm talking about MAPS simulator. And why MAPS simulator, right? And I have two reasons for that. One, it can basically satisfy the requirements from the standpoint of agriculture. From our standpoint, we want the simulator to simulate uneven terrain, of course, because the field is not flat. And also we want to have a preciseness in the simulation of how sensors interact with the world. And also, we do have requirements in terms of soils. We do have different soil types which affects how tires interact with the environment. And the MAPS, this simulator can deal with those. That's the first reason. Second, this software is completely open sourced, meaning it's transparent. You can modify, the source code to suit your need. And the more importantly, you can bring your need to the discussion table, and we can work on it together, and we can incrementally improve the simulation, so we can make the simulator we can make the simulator work well for the agricultural scenarios. So that's why I'm proposing this simulator. But you might ask, okay, this sounds great, but what kind of stuff that you can exactly do with the simulator? I think the best way to answer that question is actually to look at the use cases of MAPS in general. This is a list of use cases that are proposed by the developers of the MAPS, which is the Center for Advanced Vehicular Systems, which is the research institution at MSU. And if you look at these use cases, you probably immediately start realizing that, these are use cases of, these are something that we want to do in an agricultural scenario, right? So this basically indicates that you can easily apply MAPS to agricultural scenarios. So I think by this point, I guess I kind of gave you a good amount of motivation, to start thinking that, okay, to start thinking that, like, what maps can exactly do, like you are probably interested in the details of the functionalities of maps. So in the following slides, I'd like to kind of go over the details of the functionalities of what maps can do. So let's start with the environment simulation. So maps has a good amount of flexibility in terms of the simulation of the environment. Well, you can define, your field with arbitrary roughness, and also maps can automatically generate terrain for you, which is especially attractive when it comes to machine learning development. And also as other simulators, you can change the weather, you can change the cloud cover and so on, and of course you can change the date and the location, which affects the position of the sun. And also, of course, you can place whatever objects in the simulation environment as long as you have 3D data. And also, this is an important slide. Maps already has sensors, simulated sensors, that are often used in the agricultural autonomous system. So we have LiDAR, RTK GPS, RGB, and RGBD. They are already available for you, so you don't have to develop something from scratch. You have something to start with. So you can just use those sensors and you can do whatever you want to do. And there's a strength in the simulation. So you can also maps can automatically segment data for you, so you don't have to like segment data to train your machine learning model. And I think I have like example images. This is the cotton field that I created in the simulation environment, and I took the images with the background under different cloud cover. You can see that there's a change of the brightness from one cloud cover to another, right? And also there's one more important thing about maps. It's very user-friendly. It's super easy to install on Windows and Linux. I think it takes less than 5 or 6 minutes for manual work, to do the installation, and you won't probably have a lot of errors. And also, even though it's written in C++, well, it does have multiple APIs with which you can access to the features. I'm basically used Python API to access the features of maps, and so far no problems at all. And actually, I think I still have time a little bit on this. And I'd like to kind of spend a little bit of time to touch like a list of like research topics that we are doing using maps. There are like about 3 research topics that I'm working on. The first one is the cotton ball detection model development. So basically what it tries to do is that it tries to answer this question: can we develop a cotton ball detection model using the simulation images, and can the model produce the same performance or better performance compared to the cotton ball detection model trained on real world data, with the purpose of the reduction of the burden of the data collection. And also I'm planning to do the sim to real transfer of the navigation algorithm, which basically where I'm trying to train the navigation algorithm in the simulation environment and transfer the algorithm to the real world. So you don't have to do data collection and then train the model in the real world, right? And the third one is more like for the data preparation for maps. If you want to have a agricultural fields in the simulation environment, of course you need some kind of crops, 3D object of crops, right? But the thing is, acquiring such data is a little bit time consuming. Like last year, what we did was we transferred cotton plants from the field to the lab and take images and get 3D data. This is really time consuming. So what we want to do is that using the Amiga robot from PharmNG, we'd like to get data in the field and then automatically create the 3D cotton objects, so you don't have to spend time on the data data preparation for the simulation. So that's what we want to do. And I think I forgot to mention one thing. So maps is not primarily made for the agricultural cases, but as we saw, there's a big overlap between the use cases of maps and also our use cases. But if you start working on it, once you start working on it, probably you will notice that there's a small tiny gap between what's been already implemented in maps and what we actually want to do. If there's a such case, well, again, this is open source project. So what you need to do is just create an issue on GitHub page and just post the issue, and then we can work on it together, and we can start improving the map simulator so it can fit our need. And we have the main developer of maps is very fast when it comes to the response, and then he's very quick worker, so we can easily kind of respond to your need, and then we can kind of incrementally improve the simulator. So I think I still have time. Actually, when I practiced yesterday, it took actually 12 minutes, but well, 2 minutes remaining. I think one last thing. You might say, well, simulation is not perfect. Well, it's actually, no, it's not perfect at all. I mean, when you compare the images in the real world and also the images taken in the simulation, you see that there is a slight difference in terms of the shape of the histogram. And this is called something called a simulation and real gap. Well, simulation is not perfect, so there's a gap. But if you want to reduce the gap, we can do so. We do have a lot of post-processing techniques. We can do histogram matching, to make the distribution of pixels, pixel values similar to the real world, and that would be one of the approaches, to reduce the sim-to-real gap. And we have tons of researches that are done on this topic. So I think there is still, you can be positive about the sim-to-real gap as well. All right, he's studying. So let's wrap up this presentation. First of all, I'd like to say thank you to Matrix to financially support my researches. I'm very grateful to that. And we have tons of great collaborators from CABS and our lab and also AAI. And I think this is the most important slide. I think I made a mistake actually. You got to cover one of the QR codes to read the other QR code, but on the left you have a QR code that leads you to the GitHub page of Maps. And you are very welcome to play with it and give feedbacks on GitHub. And we are happy to kind of, my ambitious goal is that to make this simulator de facto standard for the simulation in agriculture scenario. So let's, if you'd like, let's improve this simulator, and then let's make it like the agricultural, let's make it a simulator that works great for the agricultural scenarios. And that's it. Thank you very much.
So I have a quick question.
Yes.
So I see the great value of having the ability to replace parts of your system with a synthetic approach like this, right?
Yes.
It allows you to start developing the tool chain, right, without having to have all the pieces in place from the beginning.
Yes.
But it isn't a universal solution to everything. There will be environmental conditions and things that are sort of unknown. I don't know, the dynamics of dust and things like that, your team might not have studied well enough yet. So are you guys thinking of putting out some kind of implementation kit, some notes and saying, what you should do, what you shouldn't do, how to use this, and so forth?
Strong documentation is everything.
Yeah.
So we don't have, first we do have good documentation in terms of how to use the simulator, but we don't really have a documentation regarding guidelines of how to use it. And my feeling is that we can't replace the physical testing at all completely. So what I kind of propose is that at least we can use this simulator to compare for example, to compare the performance of the prototype algorithms and to get some kind of feeling about what you are trying to build. And you can kind of play with it in a simulation environment and get feeling and then put it outside.
So that kind of expectation management is very important, right?
Okay.
Because otherwise people might use it for the wrong thing,
That's right.
fail, and then blame your product for it. They're very much human nature. So just consider doing that, providing guidance. Thank you.
Thank you.
Thank you very much.
I have a question.
Sure.
Two short ones, actually. First of all, thank you for the presentation. Is there any support for manipulators for like mobile manipulation tasks? And secondly, do you have differentiable physics in the simulator?
I got to be honest. I didn't go that deep into the vehicle, like physical simulation part yet, but I can definitely get back to you. Actually, today, the main developer of the maps is supposed to come here today, but he seems to have health issue and he couldn't come. I can definitely get back to you, or I think we can start discussing about it on GitHub, and so it can benefit you others.
Please do exchange everything. Thank you again. So next speaker, advancing SLAM in agriculture, in comparative study of NERF and traditional approaches.
Hi everyone, I'm Paris Du. I'm first year graduate student working under Dr. Zhang's supervision at ABU Portland. Today I'm going to talk about advancing SLAM using NERF, which is a neural radiance network. So first I want to talk briefly about SLAM. What is SLAM? So when we have a robot or a device moving in agricultural field, to be fully autonomously, so we need it to build the map of its own and know where it is in the map, to know both position and orientation. So we use a SLAM, and we rely on some sensors like cameras, LiDAR, IMU. So cameras we use for visualization. The LiDAR is more precise, but it's costly, so we try to use cameras these days, and we use IMU for motion and orientation. The traditional SLAM algorithms, they have some processes after they they take some data from the sensors we use. They do some loop closure trackings, and post-graph optimization to give us something like the output there. So this is the 2D map. I'm working on 3D map, but the same process. So why SLAM in agriculture? So we are trying to be fully autonomous in agriculture. So we need SLAMs for several applications that we have in agriculture, such as we need to be precise in a spraying, we need it for phenotyping, we need it for harvesting. So it's very useful. And the other thing that we have in agriculture is it's unstructured, dynamic environment, which has some challenges for us when we go in navigation part. The repetitive textures it has, the illumination issues from the sunlight we have, and the terrain itself, it can cause us some challenges here. So we try, nowadays, they try to advance the SLAM, they try to improve a SLAM using neural radiance fields, which is a deep learning algorithm. They try to use it as a hybrid algorithm, both SLAM and NERF, and to optimize the 3D map builder that creates from NERF SLAM. So one thing that is good about NERF SLAM is its continuous function. It doesn't rely on key points that were before used from traditional SLAM like RTAB-map or ORB SLAM, and it actually tries to minimize the reconstruction loss, as it could use RGBD images that I'm going to show when we go further. So the goal is to have a robust 3D map of the environment from inputting 2D images. For this research, I used one RGBD dataset for both RTAB-map, which is a traditional algorithm, and NICE-SLAM, which is a well-known NERF-SLAM algorithm. So I can see that I used subscribe to related nodes. So these are ROS nodes. I briefly talk about ROS is robot operation system, which is a middleware system that we use in robotics to make us to communicate with different sensors and algorithms, especially if you want to do real-time processing. ROS can help us in that way. So we use ROS in this project to record and replay data, and also to launch our both algorithms. And we, after doing that, I'm getting the output of both algorithms. We do the comparison. I try to use it both visual and numerical as we go. So what is the data set? The data set is which I used is Transcentia data set, which is an open source data set. It is RGBD, it uses RGBD images. The sensors that are used is a Z2i stereo camera, IMU, wheel encoders, and GPS. So this is the robot they use. It's a very small robot, and it goes in a real cornfield. So why did I choose this open data set? Because it has diversity in growth stages, in different illumination, lighting conditions, and also seasonal changes that are all of our challenges in the agriculture. And the data format is ROS-back, which gives us good opportunity to just launch them in the algorithms. The thing that is important about data is that data synchronization. That is very important here. I've shown here that the synchronization between two stereo cameras and two stereo eyes actually, and the left camera and the depth camera is good. It's actually about 2 to 10 milliseconds. It's not perfect, but it can give us something. So if we don't have the synchronization, we can't get anything out of the algorithms. The data has 4 scenarios related to different growth stages of the corn. So I chose scenario 3 and scenario 4. One very good situation, one very bad situation for algorithm. So scenario 3, it goes through 4 rows, and the plants are in 13 inches height. And scenario 4, just 1 row, which is very bad for algorithm, actually like RTAB-map, which is based on loop closure. And the plants are 20 inches height, and somehow they block the view of the camera. The data format is 480 height, 640 length, and 3 channels RGB, and unsigned integers. So we have the intensity that you can see here. So I'm going to show you a little demo of RTAB for scenario 3, which is a good scenario for traditional algorithms. You can see that the robot is moving through the rows, and the odometry is working fine. The below is the 2D map. It's building, and it's building the 3D map there. So I'm going to show you the point cloud map that it builds after running the algorithm. So after running that on our data set, we can see that the RTAP map makes that 4-row point cloud map. It's working for scenario 3. Now scenario 4, which is which we are going through NERF instead of RTAP map. So you can see here that we have drifting issues. The point cloud is not precise. The view of the camera is blocking by the plants, so we can't get good results from RTAP map. So one of the things that cause these not precise good results from RTAP map is the odometry gets lost when we have the blocking view, because RTAP map is based on the visual features, and it's related to tracking key points that I said in my first of my presentation. And so when it blocks the view, we can't get anything out of RTAP map. So we go to NICE-SLAM, and we can see that when we have the RGBD images, it generates the 3D view. So here I show a small view of NICE-SLAM just as a demo. We can see that it makes the corn row. This is the row that it goes through. And beside the visualization, we need some numerical outputs to compare these two together. So the thing that limits our project is we don't have any benchmark point clouds data set in agriculture. So we chose absolute trajectory error and root mean square error to compare these two together. You can see that for scenario 3, both algorithms, however, NICE-SLAM is better. They are both working, but for scenario 4, which had some issues, we can see that RTAP map can't get us anything. It has 45 meters error, which is very bad. What NICE-SLAM is working. So even though we had a very small data set for NICE-SLAM, we can see that NICE-SLAM is working perfect. The challenges that I'm going to further look for it is after some frames, the NICE-SLAM odometry is getting worse, so I'm going to work on it. And because we don't have the data set has synchronization issue, for this year I'm going to collect my own data set using Amiga FarmNG robot and the WPOE camera, and using the RTK GPS as ground truth. Thank you. So as acknowledgement, I'm going to thank MAPAS, which are supporting me financially. And thank you, my professor. Thank you.
Please. So good presentation. I wonder, did you use IMU or so? Because since you have stereo, right? You have that. Did you use that, or you use only RGB?
I use RGBD, RGB images and depth images, but we can use IMU too. But I didn't use IMU.
Okay, so then the GPS was only used for like a ground truth, right? But that was RTK GPS.
No, I'm going to use RTK GPS in my research, but this one was GPS only.
Okay, thank you.
One more quick question.
Yes. Do you think if you use, like, follow-up question, if we include GPS and, for instance, IMU, we can mitigate the area that 45 acres that is over there, probably if we use another sensor like IMU or GPS, do you think we can mitigate it, eliminate that area?
I don't think so, because our map is visual-based algorithm, so it is dependent on the visual side of the sensors it gets. So I don't think so, but maybe for nice snap it can help.
All right, thank you very much. Teacher Lagimbo. So he's going to talk about leveraging graph neural network and Neo4j for Gaussian Gilling prediction.
Good morning, everyone. My name is Peter Mimwa, and I'm a PhD student at the University of Georgia. And my today's presentation is about how you can leverage graph neural network and Neo4j for quantum. So first thing first, why do we need to predict the quantum? So we need to predict the quantum because we know that cotton is the globally, it's the #1 producer of the fiber that we use in the textile industry, and it supports the economy and the livelihood of the people who are all over the world. So we need to predict the yield so that we can optimize the resources to know how much fertilizer we need to put in the field so that we can optimize too many of the less. And also, it can also help us to forecast the market to know, okay, by estimating the yield, we know the demand and the supply so that we know if we need how to better finance, how to better manage our finance, like not to use too much resources, because if we use too much resources, maybe the prices go. It means that's a loss to us. And also we need to be able to predict yield so that we can manage our field. For example, if you have much more field, the requirement of the field is different. This field need more water, we need more fertilizer compared to the other. So there has been a challenge. So the challenge is now we know this modern technology. Now with the use of this modern technology, a lot of data are being generated. And most of this data are interconnected data. For example, we have this technology that we can generate, we can generate the weather data, we can generate the soil data, we can capture the satellite. But we know that for the yield perspective, we know, for example, yes, it's weather, it's affect the soil, and the soil will also affect the yield. So these data are interconnected. But the method that people we have been using now is a traditional method is they are not able to capture this interrelationship between these two data, because the way they settle their data, they put it in a tabular form, but they cannot capture how these two data are interconnected. So to solve that, for this study, we decided to use the graph neural network, which is it's a deep learning model which has the capability to model and analyze the data that can be put into the graph structure. And this graph neural network models network is able to do that because it can capture the interaction, the interrelationship or the interaction between this data by using this method or algorithm. It's called the message passing algorithm, whereby each entity, for example, waves and the soil, they are presented into the node, and using this message passing algorithm, it can be able to understand each other, so it can formulate the interaction, which can able to understand each other, which can capture the interaction between these two. And also, we use the graph neural network. We use the graph database, which is the Neo4j, because we wanted to facilitate the interaction between this heterogeneous data source, so to allow unified representation of the diverse data source that we have so that we can effectively analyze. And this Neo4j, as I said, is a graph database which is implement property graph model, which is store the data in the form of the graph, in the form of the nodes, and edge. So nodes are the entities, and the edge and the relationship. So based on this, we formulate this hypothesis that by being able to integrate this heterogeneous data source into the graph data algorithm, we'll be able to enhance the cotton yield prediction. So to do that, this is how we did. So first we collected the data, then once we collected the data, we put them into the graph database. Then once we put them into the graph database, we retrieve the data from the graph database into the graph neural network model, whereby we train it, then the training we are able to predict the yield. So for the data collection, we use different devices to collect the data. For example, we use Rover, whereby we are collecting the images. We also use the manual method of collection, as you can see in the video. We are collecting the data, and also we use drone. So once we collected this data, then we put the data in a graph. In our graph database, which is the Neo4j. So for the purpose of this presentation, because this is the ongoing project, we didn't put all the data into the database. So the only data that we put were the plant features, which the plant feature that we use were the height that we are measuring for the plant, and also the chlorophyll index that we are measuring for the plant, and that information.
No, it doesn't point at that, you have to use the mouse. You use the mouse.
And so for the plant information, we put in this, we put the information in this node, and also we have the soil data that we collected, we put in this node, and the plant feature we put it in this node. So you can see we created this the relationship, like the plant has a plant feature, the plant also has a plant soil data, and the plant has plant yield. So with the graph neural network, it can be able to understand this interrelationship and be able to predict it. And on the right side, this is how it looks like when once we retrieve the data from the database. We use this package is called the network X. So once you retrieve the data from the database, it looks like that, and from there you can train the neural network. And I think I forgot to mention, so for this plant, the way we collected the data, we had 3 fields, and we had 2 fields, and on each field there are plants that we are monitoring. So for each plant, we are also collecting the GPS pointing from those individual plants that we are monitoring. We are collecting all this information. So once we have all this information, then what left was for us to train. And so for this particular, for now what we did, the architecture that we use the graph attention network. So we use the graph attention network because it has a mechanism whereby, it has attention mechanism whereby it's able to prioritize which nodes are more important than others, so that to make a better prediction. Because as I said, this graph neural network, they use the message patching algorithm whereby like these 2 nodes, they learn from one another by updating their information from one another. So if this node and this node, they aggregate information so that they can learn the information about the whole graph. But with this graph attention network, with the attention mechanism, it's able to know which node is more important than another. For example, if there are 2 plants, and they're close to one another, so the soil information from this plant, which is close to the other plant, is more important in predicting the yield of this plant compared to the plant, the soil information that for the plant that is far away from another when the soil are not similar. So based on this model, we have this. So this the prediction that we have. So far, our test accuracy was 81%, but because we only used the few data that we had, we hope to improve this. And this is how we train. Of course, we train up to 5,000 a pop, which I think maybe you can ask why you use all this pop, but there was no. There's like it's only stopped learning from here. Of course, we could have stopped there, but yeah, decided just say 5,000, but we could have stopped there. So based on these results, what you are planning to do now, we want to incorporate additional data that we have, the data from the weather, because we have a weather monitoring station. We also want to include the data from the drone. And here we only model the effect of the plant, but now we want to incorporate the effect of the field and the plot, because we had two plots, we had two fields. One was irrigated and another one was not irrigated. So we have to incorporate that component of irrigated and non-irrigated. And for the plot, there are plots that we are monitoring for the whitefly and those that we are not monitoring for the whitefly. So we also want to add the component to see how it can how it can influence our prediction. And in the case of the optimizing model, we want to do more feature engineering, whereby we want to identify among the data that we have which one better predict the yield. And we also want to improve the tech that we have so that in case of the overfitting. And we also want to explore another models such as this is called graph aggregation, graph sampling and aggregation, and heterogeneous graph transformer, because the graph attention network that we have, it uses the technique which is called a transductive, whereby it has to, when you develop the model, it has to learn from all the graph. All the nodes have to be on the graph so that you can be able to predict. But with the graph search or graph sampling and aggregate, not only necessarily all the information that you have, it has to be on the graph so that it can be able to predict. So that's what also we're trying to use that. And we also are trying to use the heterogeneous graph transformer because our data are heterogeneous. So by using this method, it can improve our prediction. Thank you.
Good presentation. Could you go back to the slides where you have the graph, where you have the plans and plan features and also the soil? So how did you, is this directed or not? Because you only have a directional edge from plan to plan feature, and you have another edge from plan to plan soil data. So plan feature and plan soil data, they're disconnected to me, because you only go from the plan to the other two sides. But actually, to me, intuitively, soil data is kind of influencing the plan feature. So how did you model it?
Yeah, I think that's a good point. So here I showed this directional, right? But when I was modeling, I was using the PyTorch geometry. So when I was modeling, I was ignoring this direction. So I was using an indirection for modeling.
Just curious, how are we in the growing season and the model make the prediction? At what point in the growing season can the model make a prediction?
When in growing season the model can do the prediction?
That's a good point. So the end goal of this is to have a time series whereby, because we are collecting data a weekly, but for what we did here now, we took an average. So for all the data that we had, we averaged, and then we use that average to make a prediction.
I think I will talk to you after this presentation. I have more questions.
So very nice presentation, and I feel like that this neural network methodology would be a good use for local, plant impacts or looking at the local estimates. My question is, do you have any information on how much is the computation power that it needs for this type of technology to be in production? For example, if somebody would like to use that, or this methodology would be used in some kind of app, is it going to be highly computational intensive, or is it readily available cheaply for that?
Yeah, that's a good question. So I think it depends on the first of all the price that we use. But because we had another study whereby we are comparing the computation between different, like for example here we have a new here, but we are like the pipeline from data storage into the prediction, what's the computation. So what we found is
How long it take to run an average size data set?
because for now we didn't add any images to this time.
10 minutes?
Yes.
All right, less than that. Thank you very much again. All right, our next talk, speaker is here. Evaluating the complete processing workflow of machine learning-based crop yield estimation approach using multi-sensor data from US for corn and cotton. Please go ahead.
Yeah. Hello everyone. Good morning. Welcome to the presentation. So I'm Mohammad Abdushaid Rafi, a PhD student at Mississippi State University in the Electrical and Electrical Engineering Department. I was supervised by Dr. Volkan Senyarek and Dr. Adi Gurbuz, as well as guided by Dr. Adeli and Jan Bohman. So let's start with the presentation. So this is the outline that I will be presenting today. So the research objective that we're looking into is definitely exploring multi-sensor data to comment on the yield prediction of cotton and corn crops, as well as we want to give our verdicts on the different steps of the processing in terms of the most optimal feature selection process, machine learning models, and validation techniques. If we're looking into the background and motivation of our work, definitely the first thing is to inform the yield beforehand of our time, so in the critical growth stage of the crops, as well as it helps with the optimization of the agricultural resources, and also it helps with the food security, informing the forecast of the food shortages and the food surpluses. So one specific motivation comes why we're looking into corn and cotton is if we look that in 2023 in Mississippi alone, that in 1.2 million acres of land were harvested with these two crops, providing a total production value of almost $1 billion. So these two crops are in the top 10 agricultural crops in the Mississippi and United States. So let's move forward to our proposed processing flow. So we start with the data collection from different sensors. Next, we'll look into the data extraction, the features that we have collected. And from there, we also looked into the different feature selection options and tried to go for the best one. From there, we actually employed several machine learning models. And finally, we do the result validation in terms of different matrices, and we try to give a verdict on each of these steps. So if we look into the data collection first, so we actually collected our data from a 2.3 hectare area. So this is known as North Farm in Mississippi State University. So the duration was 4 years, from 2020 to 2023, and we focused in the crop growth period between April to October. And as we can see, so in our field area, there is 2 field sections that were alternatively cultivated with corn and cotton. So, and each of these rectangles actually representing one crop plot, which consists of 4 crop lines. So, in terms of data acquisition, so we used a MicaSense Red Edge MX multispectral camera from US, also a TrueView 515 LiDAR from US. So we used a Mississippi Extension Delta weather station that is only 300 meters away from the field. And also we have used several soil moisture probes in the field for collecting soil moisture, for collecting soil properties. And so the frequency of our data collection is once every week. So we have 1 set of data per week for the corn and cotton growth. So our data collection frequency, so over the years we can see we have collected almost 50 set of data from multispectral US, more than 30 flights from LiDAR US, and so the number of soil moisture probes actually varied from year to year within these periods. So for the features that we have extracted from different sensors, so we have collected 34 features from 4 major sensors over the 22 weeks of data collection. And so from the multispectral camera, we have extracted 9 different vegetation indexes and also canopy cover information. So from the LiDAR, we have plant height, entropy, and Curtis's information. Soil moisture probes gives us soil moisture and soil temperature information. And the weather station, we have extracted 15 different weather features from there. So one important thing is that in terms of ground truth data, we have 60 plus in those 2 field sections, 30 plus each. And so for over the 4 years, we have only 1 yearly yield value, so that gives us 235 set of ground truth data. So these are the vegetation indexes that we have extracted. I will not go into details of them. Similarly, so the LiDAR features that we have collected, as well as the weather feature that we have collected from the weather stations. So I will take some time to talk about this one. So these are the ground truth distribution of the yield that we have. So the blue one representing 2020, the red one 2021, yellow for 2022, and purple for 2023. So one thing we can notice from here is that the difference between the weight level of cotton and corn, as we're looking into 2 different crops, and also the value of yields in 2020, 22, and 23, they're in a similar stage. But if we look, if we focus for both the crops, we can see the yield is actually dropping compared to the other 3 years. So for the feature selection method, we have actually went over several feature selection techniques. So supervised feature selection techniques, and the 3 that we have focused on was Pearson correlation, feature elimination wrapping, and group-wise feature elimination wrapping. So firstly, we've looked into the Pearson correlation result, and so I have not included the result in here, but the result that we get from that correlation table was inconclusive in terms of selecting which features should we shortlist. So the next, we examine basically two recursive wrapping methods, and comparing between those two, we have found, so the result was very close, but in terms of overall performance, we selected the groupwise elimination wrapping process. Here is the process of groupwise recursive elimination. So we take all the 34 features and we separate them into 5 major categories. And so the way it works is we keep all the other categories constant, where we select one feature from the first group, let's say, and then we use these features as input through a machine learning model and a performance matrix to see the performance in terms of the yield prediction. And so similarly for all the features in that group we test, and finally we, based on the importance, we select a specific number of features from those groups. And so going through all of them, we actually selected 11 features for corn and 11 features for cotton, finally, to move on with our yield estimation. So for the machine learning algorithms, we have looked into 3 different machine learning algorithms. So feed-forward neural network, long short-term memory, and random forest. As we plan to look into some complex models, one thing that I already mentioned is in terms of the ground truth data, we already have a limitation with only 240 ground truth sample. Now, as we all know that machine learning models actually thrive on a bigger data set. So in terms of our input features and input data that we have a lot of data that would be great for our model. But one thing is that with the limited number of ground truth data, we had to go with some simpler machine learning model for our research at this point.
Wow, man. Because you don't look at it.
We also did hyperparameter tuning, and in the table you can see the different optimal hyperparameter for the models. And so finally, if we go into the result evaluation, so the 2 error matrices that we have used are the RMSE and mean absolute error. And as I mentioned, the difference between the 2 crops or weight levels, so we have to look into the percentile value of these 2 error matrices. And the 2 validation methods that we have used are the field-wise. So we looked into corn and cotton, and year-based from 2020 to 23 on the 4 years. So first we looked into the field-wise result validation, and we can see that the results for all the 3 models and for both the corn and cotton fields, they are very similar, providing around 80% accuracy. And if we try to figure one machine learning model in between, we can comment that the LSTM is performing better than the other 2 models. And looking into the year-wise validation, one thing that we have already mentioned, that in 2021 the performance dropped due to a drought that happened in the critical growth stage of the crops. We can see that even if the other 3 years are performing better, the 2021 the performance dropped. So in terms of qualitative performance, we can again see that the estimated and the ground truth yields, they are very much similar in 2020, 2023, but in 2021 if you see the performance dropped again due to that drought period. And we also tried to look the correlation, and so it is not the best, but it is satisfactory so far. And finally, in order to conclude, we can say that the approach is an effective approach, giving us a promising accuracy of 80 to 85%. And if we try to comment on the machine learning model, we can say LSTM is performing better, providing as low as 9% accuracy. And in terms of the 2 validation technique, we would suggest to go with the field-wise validation. And if we look into the 2 fields, their performance is similar, but in terms of year-wise, currently we're seeing a drop in 2021. Using the LiDAR derived features, as well as like analyzing the end-to-end processing flow would be some of the novel part of our research. And in order to talk on the limitation, I already mentioned about the limited ground truth samples. So one thing that we're currently working on is to include a larger number of ground truth information, whether it's from the field in real scenario, real field scenario, or synthetically generated, as well as looking into different cover crops in order to explore different fields, as well as in the critical stages. So these are the references.
Okay, thank you very much. Try bi-directional SDM and transfer. Based on what you're doing, they're going to give you the bi-directional SDM and then transfer. Maybe one quick question. Please.
You said like you used time basis indices, and since you had different flight dates, how do you like which flight date you picked, or you extracted basis indices from all flight and did the feature selection?
So we have actually only one flight over a week. So we looked into like from the planting of the crop. So we have 22 weeks until harvesting. So we just have one flight over 1 week, and we take that value.
So you have 9 basis indices for each week.
Yes.
All right, thank you so much. All right, next talk. Comparative study of deep reinforcement learning for crop production management. Christoph takes this on.
That was an arm or the data started you harvesting or you want. So I was basically making these talks for the information. You get that from
Hello everyone, my name is Joseph Baldetis. I'm a mathematics PhD student at UT Arlington. And the title of my presentation is Comparative Study of Deep Reinforcement Learning for Crop Production Management. So the program I did my research in is the USDA ARS UT Research Apprenticeship Program in the summer of 2024. And here are my collaborators.
More slides.
So the outline for the presentation will be first I'll give an introduction, we'll talk a little bit about reinforcement learning, the crop simulator environment, and then we'll go over the two RL algorithms in study, and then we'll go over the numerical experiments. Okay, so the problem that we're looking at today is crop management. This is defined as a series of logical actions a farmer makes to reach some certain crop production goals. And this is difficult to find optimal crop production policies that can handle the dynamic situations that happen on a crop field. And recently researchers have started looking at machine learning methods such as reinforcement learning to learn optimal dynamic policies for crop management. So the recent research in this field has been centered towards developing crop simulator environments in which you can test RL algorithms, and also on the testing of different RL algorithms to see which ones work best for crop management. In particular, two algorithms, proximal policy optimization or PPO and DQ network or DQN, have shown promise on a particular crop simulator environment called GEM-DSAT, and these are the two references for those two methods. And our goal is to test those two methods using the same environment settings to get a fair comparison of the two methods on the GEM-DSAT environment. So the way that reinforcement learning works is you have an agent that interacts with an environment, and you have a sort of loop of trial and error where the agent will make an action in the environment, and the environment will spit back a state and a reward for which the agent to learn. And this image here shows the reinforcement learning setup in the context of crop management. So the agent in this case will be a farmer and the environment would be a crop field. Every time the farmer makes an action, such as applying an amount of fertilizer or irrigation, the crop field will provide certain state variables and a reward so that the agent can learn how to better make actions in the crop field. So the objective of reinforcement learning is for the agent to optimize an objective function, which is the expected value of cumulative rewards. So the agent wants to maximize his overall rewards in an episode, or in this case, a growing season. In reinforcement learning, we want to learn a policy or a strategy, and that is going to optimize this objective function here. And there's three main types of approaches for reinforcement learning. There's policy-based methods in which you estimate the grading of this objective function. There's value-based methods in which you try to learn a value function, which will give you a measured quality of a state. And then there's actor-critic methods, which do both. So the GEM-DSAT crop simulator environment is the environment we focused on for this study. It is the default simulation is a maze experiment, and its simulation starts at the date of planting and ends at harvest, or if there's crop field. And you have different options for weather. You can have random weather, you can have non-random weather, and then the environment provides three different problems for reinforcement learning. You can have fertilization, where the agent is applying fertilizer amounts. You have the irrigation mode, where the agent applies the irrigation amounts, and then you have the mixed mode, which where the agent can do both at the same time. So for each of these modes, you have different reward functions. And these are, for the first two, these are the default reward functions. For the fertilizer problem, you have this function, reward function here, where TRNU denotes plant nitrogen update, and for denotes the amount of nitrogen applied at time step t. And for the irrigation problem, we have this reward function here, where top WT denotes the change in above ground biomass, and EMIR denotes the amount of irrigation that was applied at time step t. And for the mixed problem, it just gives you a tuple of those two values. And this is, if we want to run reinforcement learning for the mixed problem, we actually have to use a different reward function, because most algorithms work using a scalar type of reward function, whereas this is a vector. So we'll see that later. So now we'll go over the two methods that we studied for a DeepQ network. It's visualized in this image here. So you're training a neural network to take in a state and to output values for each possible action. And the agent wants to pick the action that gives the highest Q value. And because of this restriction here, for a DeepQ network, the action space needs to be discrete. So because the GEM-DSAT environment has a continuous action space, you need to discretize the action space. And this is how we did it here, which is just following the reference of the paper. Proximal policy optimization works in a similar way. It's an actor-critic method, but the way that this type of method works is you have two neural networks. One trains the value function. The value then informs the policy network, and then you have this sort of loop that you train iteratively. Value function affects the policy network. Policy network is then used to inform the value function network, and training is done that way. And I forgot to mention, for DeepQ network, we use the implementation from this reference here. We've got Wu et al. And for proximal policy optimization, we use the stable baselines 3 implementation. And a key innovation with this method is you have a clipped loss, which prevents your updated policies from being far away from your old policies. So here's the experimental setup. We use the default parameters from their methods' respective papers. We use the default reward functions of the environment, but for the mixed problem, we use the reward function from Tao et al., which is shown here. And for testing, the evaluation metric we used was average cumulative rewards over 1,000 test episodes. And we tested against two baseline methods from Gautron et al. The null method is will just always apply zero irrigation or fertilizer, and the expert policy is a static policy which is informed by experts, and is actually the policy used on the original experiments in 1982. So here's the our numerical experiments. First box shows the results for the fertilization mode. PPO does the best, and then the expert, and DQN actually does last here. I found out recently, a few days ago, that the reason for this is because the action space, the way it's discretized, is it's allowing actions that are too large. So if you actually change the action space to between 0 and 50, you get much higher and more competitive results. Still less than expert and PPO, but much better than it did here. The allowing it to have higher applications of fertilizer makes its the testing have a lot of variance, and that affects the results. For the irrigation, we see similar results. PPO is doing the best, expert does second, and then here the DQN method is much more competitive on the irrigation setting. And then for the mixed setting, expert does the best, and DQN this time is outperforming PPO here in terms of average cumulative awards. And for some reason, PPO learns a very scarce type of policy. We'll see in the next slides. It's almost identical to the null policy, and the results were not very good on this book. So here, 2D histogram showing the applications of fertilizer and irrigation. Darker areas correspond to higher frequencies. And then on the x-axis, or horizontal axis, we have days of the growing season. So these first two boxes show the fertilizer results. PPO, it's this box here, and you can see that it sort of wants to apply fertilizer the first half of the growing season, whereas the DQN method, you have these boxes because you only have a discrete set of possible actions. But it's hard to see any pattern that's happening here, which maybe is why the results are so bad. And for irrigation, we see that there's somewhat similar results between PPO and DQN. PPO wants to apply more irrigations, sort of in between 80 and 120 days of planting, and DQN has a similar result here. This is for the mixed experiment, and what I was saying earlier about PPO learning a scarce policy, it actually doesn't apply any irrigation at all during the evaluation results, which indicates that maybe the reward function, there needs to be some type of hyperparameter optimization, or maybe the reward function needs to be changed. And for the DQN network, there's a much clearer idea of what it's of the policy in which it's learning. So to conclude, we saw that the PPO algorithm outperformed DQN on the single tasks, whereas for the mixed task, DQN outperformed PPO. And the main limitation was we didn't include a stage of hyperparameter tuning during our testing phase, and that might change the results. Also, we saw that the reward functions were very, that they had a large impact on the actions. The action spaces had a large impact on the action space, plus the reward function had a large impact on the results. So we should try different reward functions in different action spaces. And then also, another thing we could try for future work is to test different types of reinforcement learning, such as offline reinforcement learning. That's it. Thank you.
I do not need to show him the 2 minutes formula. Any questions? Please.
No, really fascinating. So if I understand correctly, you were simulating where it can irrigate and fertilize every day, right?
Yes. So
but in the real world, right, there's constraints on that, and of course scheduling is one of the big things. So how do you anticipate that would change your results, or how those models would learn in that environment?
That's something that, so the way that the simulator works is every day you have a choice of planting, and you can maybe incorporate that somehow into the models where you can only, where you apply zero fertilizer irrigation on specific days, so restrained so that you apply non-zero.
Yeah, my center pivot, I can only run it once, you know,
Yeah,
it makes a circle. Yeah.
that would be interesting to incorporate, and I think just looking at the 2D histograms, you can see that there are periods where there's no applications, so I think that would be interesting to see how that would affect the results.
Any other quick, okay, go ahead.
First of all, I agree with him. I like to see the term DSAT and combination of DSAT with the declining and kind of stuff, because I'm a big fan of crop model. And I don't have a background in kind of declining and so on. I have kind of a little bit hard time in understanding the discussion and conclusion part. Could you explain in a little bit more simple terms what the especially the first point of the conclusion means?
So when I say that PPO outperformed DQN, I mean in terms of average cumulative rewards. So when I say cumulative rewards, it's an episode will be a growing season. And the cumulative rewards, every day you get a reward. Cumulative rewards means you add up all the rewards over the entire growing season. So we had 1,000 test episodes. And out of those 1,000 test episodes, we take the average of the cumulative rewards for each test episode. And comparing the averages, PPO, the PPO algorithm, its average was higher than DQN on the same tests. So that's what we mean by outperformed. There are different types of metrics we could have used, but for this study, we looked at cumulative rewards.
So PPO or whatever, like it's outperformed DQN. Oh, I understand that part. So if you can explain it, could you kind of, what does it mean in practical terms? Like, what does it basically mean?
So it means on the crop simulator GMDSAT environment that that PPO learns a policy that in general will perform, that will give you higher rewards than DQN. And we define the rewards in this way. So the reward functions, they take into account environmental impact and also yield. So you can the reward function used here denotes, or it's going to represent economic profit. You can have rewards represent different types of values, and if you care more about your profit, your reward function will change. If you care more about environmental impact, your reward function will change.
Having more rewards means that it actually learns better how to kind of increase, for example, if the reward is great amount, it basically doesn't mean that the higher reward means that it learns how to actually increase the yield?
It's learning how to maximize the reward function better. So the reward function
So I don't have background in the reinforcement lines.
Yeah, those are some of those, if you do count them, you can see how they actually affect.
Yeah, so it's specifically it's doing a better job of maximizing these rewards, and you can define rewards however you want, depending on what you value more: profit, environmental impact, etc.
You got to have it in your platform. Seriously. Please.
Do you have additional data sets that you could plug into your modeling? Because you mentioned like that Florida example, would it be interesting to look at regional differences to see the performance the same?
Yeah, so the GMDSAT environment supports other types of crops. For example, it does cotton as well. And you can input your own data as long as it's formatted a specific way. So that's something that we can also do in the future, is to test different types of crops to see if the same results happen for different crops.
Please.
Yes, so did you try to interpret the policy learned?
So that was kind of the histograms. let you sort of visualize what the policies are doing.
Yeah.
You can see like during the growing season when the learn policy is choosing to fertilize or choosing to irrigate. So that's sort of the extent of the interpretation of these models.
Okay, what about this? Did you try to align your learning policy with the actual policy?
No, but for example, there's something called imitation learning,
Yes.
which is it's a different type of sort of related type of reinforcement learning where the policies in which you're trying to imitate an existing policy, right? So that's one thing you can do. Offline reinforcement learning is another thing where you take a static data set of transitions. You can use a policy to create a data set of transitions and then train on that data set. So that would be another way you can use an existing policy to train a new dynamic type of policy.
Yes, I'm exactly thinking about imitation learning. Does that mean help you to design a better reward function?
Yes, the DQN paper actually looks at this.
Thank you.